So section 2.2, right, is titled Symmetry and Transformations. And so on page 1, we have the definition of a power function. And a function of the form f of x equals x to the n power, where n represents a real number, is called a power function. Right? So x to the n power is called a power function. The domain of the power function depends upon the power of n. All right, so here on the first page, I have the graphs of 6 power functions for n equals 1, 2, 3, 4, 5, and 6. So in the upper left-hand corner here, we have the power function for n equals 1. And so we have the equation y equals x to the first power. And you know the graph of y equals x is just a straight line. Okay? Goes through the origin. To the right of it, we have the power function for n equals 2. And the equation when n equals 2 is y equals x squared. And so here's the graph of y equals x squared, and you should recognize that as a parabola. Here is n equals 3. And when n equals 3, right, y equals x cubed. And this is the graph, it's often called the cubing function, right, because we're cubing the variable x. And, you know, up here in the parabola is U-shaped. Okay? We also call this a squaring function because x is being squared. Right? So here, the parabola graph is U-shaped. Down here, where n is odd, n is equal to 3, I say the graph snakes its way through the origin. Okay? The origin is a point on the graph, and I say it snakes through the origin. To the right of it, we have the power function when n equals 4, y equals x to the 4th. And you'll notice that that graph is U-shaped, similar to the parabola. The difference is it's flatter down here between x equals minus 1 and plus 1. And then we have the power function when n equals 5. So we have the equation y equals x to the 5th. And that graph is similar to the cubing function up here. It snakes through the origin, except it's flatter in this part of in this region of the graph from x equals minus 1, 1. And then lastly, we have the power function for n equals 6. The equation y equals x to 6. It's U-shaped again, and it's flat, getting flatter in the bottom part between x equals minus 1 and 1. So you notice on the right side, right, n equals 2, n equals 4, n equals 6. When n is a positive even integer, the graph is U-shaped. Okay? And the larger the value of n, the flatter it is going through the origin. If n is odd, starting with n equals 3, 3, 5, 7, 9, and so forth, okay, the graph will snake through the origin like it does for the cubing function. But the larger the number, right, the flatter it is going through the origin. So in mathematics, there are basic functions in their graphs you should be familiar with, right? Should come second nature to you. So n equals 1, n equals 2, and n equals 3, right, are 3 graphs that you should always know what they look like. Okay? N equals 1, right? Y equals x, y equals x squared, and y equals x cubed. Those 3 graphs, right? You should always know what they look like. You should always be able to graph those, okay? Because we work with them a lot. Okay? All right. Any questions on that? Alright, flip your paper over. And now we're going to talk about rational power functions. The rational power function is a function f defined by f of x equals x to the m over n power, right? So m over n is a fraction. Okay? It's a rational number. Okay? And the denominator and the denominator is greater than 1. So m and n, n is greater than 1. And the integers m and n have no common factors. That means that m over n, can you see that? Because I can't see that without my glasses. Can you see m over n up there? M over n can't be reduced. Okay? So, you know, like 3/27, right, reduces to 1/9. So m over n, whatever values of m and n are, right, whatever those integers are, that fraction can't be reduced. Okay? So it can't be 3/27, it has to be 1/9. Okay? As an example. Okay? Alright. Now, in the exponent on the variable x, the m over n, m is called the exponent, and n is called the power, or root. Excuse me, it's called the root. Okay. So x to the m over n, from what you know, from what we know from our knowledge of radicals, that is equal to the nth root of x to the n. So x to the m over n power is equivalent to the nth root of x to the m. M is the exponent on the variable x, on the number x. All right. So we are going to look at some graphs of rational power functions for different cases of m over n, right? The power on the variable x. So the first case, so we're going to do 9 graphs. I provided you 3 of them already. We're going to do the other 6. And the first case we're going to be looking at is where n is even and m is odd. That didn't get typed there, right? But it is n is even, m is odd. So when that's the case, y equals x to the m over n power. X is raised to an odd power, and we're taking the even, the root is even. Okay. So when m is odd, we have x raised to an odd power, and then when n is even, we're taking the even root of x to the n. Okay. So in this first case, where the fraction m over n is greater than 1, an example where m is odd and n is even is 5 halves. And 5 halves is greater than 1. The graph of y equals x to the 5 halves looks like this. Okay. And you notice that, this is the origin, right? And this is the x-axis. And the function is not defined for negative values of x, is you can't take the square root of a negative number. Okay. So y equals x to the 5/2 is the same as the square root of x to the 5th. And if x is negative, x to the 5th is negative, but you can't take the square root of a negative number. So x less than 0 is not in the domain. That's why the graph looks the way it does. Okay. In the second scenario, m over n is between 0 and 1. And so an example of m over n between 0 and 1, where m is odd and n is even, is y equals x to the 1/2, right? If m over n is equal to 1/2, m is odd and n is even, right? M equals 1, n equals 2. That is the square root function. This is another function that you should always know what its graph looks like. Right? That's the square root of x, and its graph looks like that, right? It's only defined for positive values of x. Any questions on that? When m over n is less than 0, an example of m over n less than 0 is m over n equal to minus 1/2. So we have the graph of y equals x to the minus 1/2 power. And whenever you have a minus sign in the exponent, that means reciprocal, right? So this is equal to 1 over x to the plus 1/2, which is equal to 1 over the square root of x. So you can tell from what you know about finding the domain of a function, x equals 0 is not in the domain, right? Because square root of 0 is 0, 1 over 0 is undefined. So the graph of this function looks like this. It goes to the right above the x-axis, and it goes up to the right of the y-axis. So that's the three cases for where n is even and m is odd. Any questions on that? All right, let's look at case where n is odd and m is even. So our equation y, right, if m is even, we have x raised to an even power, and then we're taking the odd root of that. So in the middle here, where m over n is between 0 and 1, right? That's the case where m is equal to 2/3. M is even. Did I say m? I meant m over n. Sorry. That's the case that m over n equals 2/3. Right? M is equal to 2, n is equal to 3, m is even, n is odd. And the graph of y equals x to the 2/3, right, looks like this. This is equivalent to the square root, or the cube root, of x squared. And you notice that negative values of x are in the domain, because when you square a negative number, you get a positive number, and then you can take the cube root of that positive number. Over here, where m over n is less than 1, we can use y equals x to the 8/3. Right? M is equal to 8, which is an even number, and n is equal to 3, which is an odd number. And the graph of y equals x to the 8/3 looks similar to a parabola. Not quite a parabola, but similar to a parabola. U-shaped. And then when we have m over n less than 0, an example of that is m over n equal to minus 2/3. Remember, n has to be positive, greater than 1. So m is equal to minus 2, n is equal to 3. And so we have the equation y is equal to x to the minus 2/3 power, which is equivalent to, because of the minus sign, remember minus sign of the exponent means reciprocal, this is 1 over x to the plus 2/3 power. Well, the graph of y equals 1 over x to the 2/3, you can see 0 is not in the domain, because you put in 0 on for x, you have 0 to the 2/3 power, which is 0, and 1 divided by 0 is undefined. So the graph ends up looking like this to the right of the y-axis, and like this to the left of the y-axis. Now you don't have to memorize all of these, but you have to, right, understand where these graphs are coming from. Okay. The whole idea is to introduce you to the idea of rational power functions. Okay. And their graphs depend upon their domains. Okay. All right. So any questions on the first two rows? Okay. So let's do the last row. If n odd and m odd, right? So both m and n are odd. So when they're both odd, we have, right, x raised to the m power is x raised to an odd power. And then taking the nth root, we're taking an odd root. So we're taking an odd root of x raised to an odd power. And so in the first case, right, where m over n is greater than 1, an example of that is m over n equal to the 7/3 power. Right? M is equal to 7, n is equal to 3. And so when we have y equals x to the 7/3 power, that graph looks a lot like the cubing function. It snakes through the origin, like thusly. In the second case, right, m over n is between 0 and 1. So an example where m and n are both odd and between 0 and 1 is m over n equal to 1/3. M is equal to 1, n is equal to 3, right? They're both odd. So we have the equation y equals x to the 1/3 power. And x raised to the 1/3 power is the same as cube root of x. So this is the graph of another function you should be familiar with, right? You should be familiar with the graph of the square root function and graph of the cube root function. And this graph also snakes through the origin, but it does it in a different way from the cubing function. Okay? It looks more along like that. And then when m over n is less than 0, right, negative, we have m equal to -1. And n equals 3, right, meets that definition. And so we have the equation y is equal to x to the minus 1/3 power, which is the same as 1 over x to the 1/3 power. So you can see 0 is not in the domain, because you put in 0 for x. 0 to the 1/3 is 0, and 1 divided by 0 is undefined. And so the graph ends up looking like this. This is the graph to the right of the y-axis. This is the graph to the left of the y-axis. Okay. And so that is your introduction to rational power functions and their examples of their graphs. Okay. Any questions on that? Okay. All right, if you flip over your page, we'll talk about odd and even functions. So in 1.4 part 2, right, we talked about x-axis symmetry, y-axis symmetry, origin symmetry. Okay. So in that homework, right, those few questions are due tomorrow night. So let's talk briefly about what we mean by an even function and an odd function. Okay. So a function f of x is an even function. Okay. If when you put in minus x in for x, so remember, right, we have y equals f of x. So if you put in minus x in for x up here, and after you simplify, you get the original function back, f of x. Right? So f of minus x and f of x equal the same thing. Then the original function f of x is called an even function. And even functions have y-axis symmetry. Remember, the graph of a function is y-axis symmetry if the graph to the right of the y-axis is a mirror image of the graph to the left of the y-axis. A function f of x is an odd function if when you put in minus x in for x, and after you simplify, the result is -1 times f of x. Remember, this is equivalent to -1 times f of x. Minus f of x is equivalent to -1 times f of x. Well, when that happens, if you have a graph, if you have a function that's an odd function, its graph, I said have y-axis symmetry. I meant has y-axis symmetry. I wasn't an English major. If a function is an odd function, right, this condition is met here, then the graph of that function has origin symmetry. And remember, graph of a function has origin symmetry if you can turn it upside down, and the graph looks exactly the same. All right, so in example 1, we're given two functions, and we have to determine, okay, whether either function is even or odd, or neither. Okay. One of three things is going to happen with every function. It's either going to be an even function, an odd function, or neither even or odd. Okay. So let's take a look at A. We have f of x. Is the door locked? You can unlock that door. There's a little button on there for unlocking. For some reason, it always gets locked. So f of x is equal to the cube root of x. Okay. So we're going to put in the evaluate function of f of minus x, right? Put in minus x in for x, and then simplify. And after we simplify, if the result is the cube root of x, then this function is an even function. If the result is minus the cube root of x, then f of x is an odd function. And if we get something, if we get neither of those results, then this function is neither even or odd. So let's put minus x in for x. And we have the cube root of minus x. Do we know what the cube root of minus x is? No. Well, let's use the properties of radicals, okay? Minus x is the same as minus 1 times x, right? You got to go down, can't go across too much. Okay, so we'll start going down. This is the product, and so this is equal to the cube root of minus 1 times the cube root of x. Okay. Properties of radicals. Now riddle me this. What's the cube root of minus 1 equal to? What is it? Minus 1, right? So cube root of minus 1 is minus 1. And minus 1 can be replaced with just minus, right? So we have minus the cube root of x. Cube root of x is equal to f of x, right? That's what f of x is. So we replace cube root of x with f of x, and we have minus f of x. Okay. So we have f of minus x is equal to the negative of f of x. Okay. Is this function even? Is our original function even? Is it odd? Yeah. Because the definition of odd is if f of minus x is equal to the negative of f of x, which is what we ended up with, okay, then our original function f of x is an odd function. So, thus, f of x equal to the cube root of x is an odd function. Okay. Any questions on how we got that? Concluded that f of x is an odd function. Well, let's take a look at B. We have f of x is equal to x to the fourth plus x to the fifth. So we evaluate the function at minus x, find f of minus x. And again, right, we just put minus x in for x on the right hand side. We have minus x to the fourth plus minus x to the fifth. Now we went through this the other day. Minus x to the fourth is equal to what? What is it? It's just x to the fourth, right? This is like minus 1, right? Just like minus 1 times x, and minus 1 to the fourth power is 1. And you got x to the fourth power. Minus x to the fifth is equal to what? We went through that the other day. Yeah, it's minus x to the fifth, right? So minus x raised to the fifth power is the same as minus 1 times x to the fifth power, which we just write as minus x to the fifth, right? So this is equal to minus x to the fifth. Does this equal f of x? The right hand side of f of x? No, right? So this does not equal f of x, right? X to the fourth minus x to the fifth does not equal f of x. Because f of x is x to the fourth plus x to the fifth. So we have to conclude, and it's not equal to the negative of the right hand side. So f of x, right, original function, is neither even or odd. Here, right, this way. F of x is neither an even or odd function. Some functions are even functions, some functions are odd functions, and most functions are neither even or odd. All right. Any questions on that? All right. Now let's talk about transformations of functions and their effect on graphs. And so the first two cases that we're going to talk about, where it says vertical and horizontal shifts, the first two cases are referred to as vertical shifts. And the last two are referred to as horizontal shifts. And I'm going to use a parabola, okay, y equals x squared, in demonstrating these four concepts. So we're going to start with f of x is equal to x squared. Okay. So in one here it's saying I have our parabola, f of x equals x squared. And if I add a positive real number to the right hand side and create a new equation, a new function, okay, the graph of this new function is the graph of our old function, the parabola, shifted up c units in the coordinate plane. So, you know what the graph of f of x equals x squared looks like. Right? It's a parabola going through the origin, right? Well, the graph of y equals f of x plus c, which in this case is y equals x squared plus c. When we add a positive number to the right-hand side, it takes this graph and it shifts it up c units. So now the vertex of the parabola crosses the y-axis at y equals c at the point 0c. Here it goes through the origin. Now it goes through the point, the vertex goes through the point 0c. Right? The graph gets shifted up c units. And then we have the opposite effect when we subtract a real number from f of x. In this case, f of x is equal to x squared. So when we subtract a real number from f of x, it takes our original graph and it shifts it down c units. So here's the origin, right? And so our original graph over here now gets shifted down c units. So this would be 0.0 minus. So the graph gets shifted down c units. Okay. When you take the original graph, the original function, the original equation, and subtract a real number from it from the right-hand side, a positive real number. So these are called vertical shifts. Okay. Tomorrow, I need to take attendance. Tomorrow, we'll talk about horizontal shifts. The graph getting shifted to the left or to the right.